Hello, my name is Daniel Hamilton. This training video covers the statistical method, specifically how it can and is used to estimate growth curves. Just before we begin the presentation, it's important to highlight what prior knowledge is useful to understand the training material. Participants should have a general understanding of the flood estimation handbook, a familiarity with the data sets underlying this, and how the statistical methodology is used to estimate the index flood QMED. More information on all these topics can be found in our free training videos, Introduction to FEH, FEH datasets, and the statistical methodology estimating QMED. All of these are available on our website. So firstly, we'll start with what this presentation will cover. So what we'll be focusing on is the estimation of the growth curve. We'll look at the single site analysis, which tends to be used for gauge sites, and we'll look at ungauged estimation, which primarily focuses on the pooled methodology. We'll also briefly cover the enhanced single site analysis, which is kind of a hybrid of those two methods used at gauge sites. Finally, we'll have a demonstration of the WINFAP software, specifically how it is used to estimate growth curves. So as you will have seen, the FEH methods are formed by two distinct approaches. You have the rainfall runoff method and the statistical method. The statistical method can be applied in the software package WINFAP, which uses data from the FEH web service to derive information for your target catchment. Unlike the rainfall runoff method, the statistical method also makes use of the NRFA peak flows dataset, which is gauging station data across the UK. So what is the basis of the statistical method? Basically, it's looking to estimate the flood frequency curve. This gives you an idea of event magnitude against its expected frequency of occurrence. So an example is shown there, which plots event magnitude in QMEX against return period, obviously in years. The way the statistical method does this is by estimating two components. So you have firstly your index flood, which we covered in a previous training video, and your growth curve. The index flood, in this case, is typically your QMED, or your median annual maximum flood. If you have a gauging station record, for example, this plot here, that is going to be the median of all those flow events. Subsequently, the growth curve is used to scale that index flood, to scale it to higher return period events. Now for ungauged sites, we don't have an AMAX series, so we can't derive our QMED. Therefore, we need to use an alternative method. As discussed in our training video on QMED estimation, this tends to use catchment descriptors and nearby donor sites. We also cannot base our growth curve on an AMAX series. We therefore need to use an alternative method, which, as we'll see, mainly involves looking at the growth curves in similar catchments which are gauged. So as we said, the growth curve is and can be used to scale your index flood to higher return periods. For instance, if we have a return period T, we would find where this return period falls on our growth curve, which would provide us with a multiplication factor to apply to QMED to derive the flow for the event with return period T. So this slide lists the techniques available within the statistical method to estimate growth curves. So if your site is gauged and you have a long and reliable record, you can apply a single site analysis, which uses the station's AMAX data and pretty much plots a line through this data based on what distribution you select to give you your growth curve. You can also supplement the growth curve you have estimated with local historical data, which may give you an idea of flood flows for events outside your gauge record. Now for ungauged sites, the principal method, or really the only method available in WINFAP, is the pooled analysis. It can be used for gauge sites as well. It's important to remember that. For example, if your gauge site is suitable for QMED estimation but does not have a long enough or robust enough record to estimate a reliable growth curve, you then may fall back on the pooled analysis. As we briefly mentioned, the pooled analysis draws on data from a network of gauged catchments within the NRFA dataset, which is selected by the software because of their hydrological similarity to the subject site. So there is a third approach, and this is called the enhanced single site assessment. So this is a kind of hybrid between the single site and pooled approaches. It takes a growth curve for your gauge site and incorporates it into the pooled analysis, giving it the highest weighting of any station. So which method should you use? If your site is ungauged, you're always going to fall back on the pooled analysis. If your site is gauged, the decision will really depend on your record length, but also the return period your study is looking to investigate. The general rule of thumb, if your record length is less than 2 times the return period you're investigating, it's likely that you should use the enhanced single site analysis. Where your record length exceeds 2 times the return period you're looking to investigate, the single site analysis option prevails. Now, when we're assessing flood flows, we're typically looking at events which are sort of your 50-year, your 100-year, your 1,000-year event. So it's unlikely we're going to have a record length that is double that amount of time, not in the UK and not really anywhere in the world. So therefore, the enhanced single site analysis tends to be used when we're assessing those flows. You may use the single site analysis if you're looking at lower order events, such as your 20-year, where your record length could be double that amount of time. When you do an enhanced single site analysis, it may be an option to compare what you do get with your single site analysis, just as a sensitivity check. So in FEH, the growth curve is derived first and then multiplied by QMed to derive the flood frequency curve, which we've already established. The FEH recommends the use of the generalised logistic distribution in general. This is the UK standard distribution to model flood flows, and it tends to be preferred because it produces the highest growth factors, so avoids or safeguards against an underestimation of flood risk. To define the generalised logistic distribution, FEH uses the L-median method to estimate growth curve parameters. These parameters will determine the shape of your growth curve. Just to note, on permeable catchments, these are catchments typically defined by having an SBR host, a standard percentage runoff of less than 20%, because so much is being infiltrated into the ground and becoming base flow. The L moments should be adjusted to account for non-flood years. Non-flood years tend to be defined by years where you have an annual maximum event which is less than half your QMed. You basically want to remove these from your record, and the flows from these years are not considered part of the flood flow dataset for the catchment you are looking at. It's quite a complicated process to remove these. More information is included in the FEH Volume 3, and there is also a permeable adjustment spreadsheet on our website, which should help streamline the adjustment process. It's available at the web address shown here. So now we'll focus on the pooled analysis specifically. So the software searches for similar catchments to your target catchment, and it automatically compiles a pooling group with over 500 station years. And that's really based on the FEH rule of thumb that the pooling group should have more than 5 times as many years than the target return period you're looking at. The target return period tends to be the 100-year event when we're looking at flooding. That's not to say that if you're assessing a 1,000-year event that you should use 5,000 years of data. It's very much a law of sort of diminishing returns once you go over 500 years, because to get more station years, you are having to bring more gauge sites into your pooling group, and those gauge sites tend to be less similar to your target catchment. So it's just to say the pooling group is made up of catchments that are judged to be hydrologically similar to your subject catchment. So how is that hydrological similarity measured? Well, it's measured based on this equation shown here, and that is defined by 4 catchment descriptors which are used to judge catchment similarity. So these are area, obviously the catchment size, the SAR, which is the standard average annual rainfall, and the FAL value, which is flood attenuation due to reservoirs and lakes. And then the final one is the FP extent, which stands for floodplain extent and is defined by the proportion of the catchment made up by the 100-year flood outline. So as you can see from that equation, area is given the largest weighting, a value of 3.2 there. It decreases as you go through the equation. So area and SAR are going to have the largest impact on hydrological similarity. So your pooling group will tend to be made up of catchments that have similar areas and wetness to your subject site, with FAL and FP extent having less influence. It's important to mention that there is a release of WINFAP due, which will incorporate some of the small catchments research being undertaken by the EA and DEFRA, and this will include a new distance similarity measure for small catchments. The equation is shown there. It basically reduces the impact of area and increases the weighting for SAR. It also removes FAL and FP extent, which don't tend to be very significant for small catchments, but it's just a word of warning that if they are, so if you have a small catchment with a reservoir in it, for example, this small catchment distance measure may not be appropriate. Which stations can be in the pooling group? So they need to be in the NRFA peak flow dataset. They need to have at least 5, but preferably 8 years of annual maxima data. We need to have an idea, a measure of the catchment descriptors, most importantly area, SAR, FAL, and FP extent. The catchments should be essentially rural. An essentially rural catchment is classed as one with an urbex value of less than 0.03, although in the software you can change that threshold. And it's important to mention that in Wales, the regulator NRW actually asks for a threshold of 0.3 to be used. The catchment area should also exceed 0.5 kilometres squared. Now, you don't have to find the catchments. WINFAP will automatically create a default pooling group from the catchment records that satisfy all of the criteria listed above. And then this can be adjusted if required. And this adjustment really is part of reviewing your pooling group. So stations that are most similar with the longest records will have the largest influence on the pooled flood growth curve. Stations can be removed based on a combination of information, and this information is provided in the software. It includes descriptive information, visual tools, and analytical tools giving you statistical measures of the pooling group. So we'll start with descriptive information. And this is a screenshot taken from WINFAP. And this is a pooling group member we've selected. So it's just giving us details, firstly, of the station, so the gauging station. So the type of gauge being used, is it a V-shaped weir, for example? Is it a crump weir? Possibly it might give details on the level at which flows come out of bank and whether this has happened in the past. If you've got significant bypassing of flows past a gauging station, then you may question its reliability to really measure flood flows. We can also look at details of the catchment, another screenshot taken from WINFAP there. So this will just give sort of a summary of the catchment, sort of its steepness, how much rainfall it receives, its geology, and any sort of human influences, sort of agricultural land, etc. If we can also use visual tools, so probably the first one to really have a look at is the single site frequency curves for our pooling group members. So these are gauge sites, so they are going to have flood frequency curves. So in this case, this is the Helmsdale gauging station at Kilfida. And basically what these blue dots are the annual maxima record, and the generalized logistic distribution has just been fit through that. And this is the growth curve for that pooling group member. What we're really looking for here is positive correlation. So the curves should be smooth and curving upwards. They shouldn't be S-shaped, and you should be careful if you see straight lines. Now this station has a negative correlation. and this indicates a negative L-skew value. Now, negative L-skew value tends to reflect the fact that the distribution is what's called bounded. Now, this may be valid. It could be the result of sampling error, for example, but it may also indicate issues with the quality of data. They do tend to be associated with stations with quite short record length. Here we've got the camel at Camelford. You can see there's not many years of data, and really the general rule of thumb is to remove these stations just as a precautionary approach. Just another gauging station there, and that's showing quite positive correlation, so we would probably not want to reject that on the basis of the flood frequency curve. You can also look at the rating curves at gauging stations. If you go to the NRFA website, that will provide rating curves, how they've been derived, the equations being used, if you want to look at that in some more detail. In WINFAP, there are also diagnostic plots available, and these allow you really to compare the catchment descriptors both for your subject site and your pooling group. So here we have area. You can see the cross marks are target site, and the black dots, which are quite hard to make out there, represent our pooling group. As you can see, they're all quite grouped together, and that's what we would expect really, because the pooling group weights area so heavily, we're going to get a lot of catchments with similar area. This is kind of a summary plot you can also get, so it shows a broad range of catchment descriptors. It also shows here the growth curves for each of the pooling group members, and the pooling group we derive is really an aggregate of all of those, and a couple of other measures there, such as L-skewness. So those are visual tools. We also have analytical tools. So these are kind of statistical measures that really measure the pooling group. So one of these is discordancy. This compares the L-moment ratios of a particular site, so a pooling group member, with those across the pooling group. And really that discordancy number indicates how conflicting the site is in relation to the rest of the pooling group. So it's listed here, and pooling group members which are discordant will be flagged in red. It's important to mention that discordant stations, whilst they'll be flagged, it doesn't mean you should necessarily remove the record by default. You need to consider what is driving the discordancy. It may be that one flood event in the record which is altering the shape of the station's growth curve. Also, if the catchment is very similar to your target site, you need to be cautious, as it may be discordant in relation to the rest of the pooling group, but it may in fact be the pooling member that is most representative of your target site. So these analytical tools really are only measures. They shouldn't be used to reject a station outright, but they are really used as a guide. Another one of these analytical measures is goodness of fit. So it provides an indication of which distribution fits the pooled growth curve best. So there we see the output of the software. A star here indicates an acceptable fit. So we can see the generalized logistic distribution and the generalized extreme both show an acceptable fit. We tend by default to use the generalized logistic if it shows an acceptable fit, even if that fit may be worse in quality to the generalized extreme, just because, as mentioned, it's the standard distribution used for UK flood data, and it provides sort of a worst case growth factors. Finally, we've got heterogeneity, which is measured using this H2 value. So if the H2 value is between 0 and 2, the pooling group is relatively homogeneous. If it's between 2 and 4, that might indicate some heterogeneity, and if it's above 4, it is strongly heterogeneous, and a review of the pooling group is often necessary. So this is the output of the software. You can see the H2 value listed there, and some guidance on what you should do. It's important to note that a pooling group might be heterogeneous. It doesn't mean that you should start rejecting stations. Growth curves are determined by many factors, and there is not always a one-size-fits-all for a certain type of catchment. So again, these measures should only be used as guides rather than thresholds with which to go about changing your pooling group. Finally, adjustment for urbanization. Now, when adjusting for urbanization, it's important to consider what impact urbanization actually has on a growth curve. And really the impact it has varies according to the target return period you're considering. And this is based on the theory that urbanization will magnify short return period floods, but has little impact on very long return period floods. So what's the reason for this? Well, with long return period floods of sort of 100 and 1,000 years, soils in an area are likely to be saturated, therefore they almost act as an urban surface already. They're quite impermeable to rainfall. Whereas in short return period floods, that's less the case, and urban areas are going to have a much larger difference than permeable areas. So taking that into account, when we adjust for urbanisation, we do the same as we did for QMED estimation. We apply an urban adjustment factor, and that will change the values for our LCV and our LSKU. And these two variables really define the shape of our growth curve. So applying this adjustment, what we tend to see is the LCV falling, so there's less variation, and that's because those shorter return period floods have got larger, where the longer return period floods haven't really changed. So there's a bunching together of those two return periods. The LSKU goes up. That's because there will tend to be a more sudden increase as event magnitude begins to increase when you apply urbanisation. So that's the end of the presentation. We'll now have a quick demonstration of the WINFAP software. So I've opened up WINFAP. We'll start by importing a catchment. So we select File, New Project, File, Import Catchment. Now the catchment we're going to use for this demonstration is a gauged catchment. That's so I can show you the single site analysis, but also pooled analysis and analysis using the enhanced single site method. So I'll start with single site analysis. So I right click on the imported catchment, I select single site analysis and site data. And this brings up the single site analysis dashboard, which provides information on the gauging station. So we have the annual maxima series here. We have peaks over threshold data set, and we also have catchment descriptors for this station. We also have descriptive summaries of the station, so the weir that's used there, the hydrometry, the flow record, the flow regime, along with a description of the catchment, so its bedrock, its wetness, its general land use. And then we also have QMED suitability and pooling suitability, which are extracted from the NRFA peak flows data set and are sort of used to assess whether a station is suitable for use for QMED estimation or suitable use within a pooling group. So in terms of the single site analysis and the growth curve, these are available here via station fittings. So we can see here that these growth factors have been derived using the generalized logistic distribution using the ALMED, the AL-median method. We can see that for the 2-year event, a growth factor is 1 is derived, and that's just to reflect the fact that the QMED, or the index flood, typically equivalent to approximately a 2-year event, so there's no adjustment when you are looking at the 2-year return period. But for obviously higher order events, you're looking to multiply your QMED estimate. The 500-year event, for example, would multiply by 4.774 to derive the 500-year flow based on a single site analysis. You'll notice that there's stars next to everything exceeding the 50-year return period. That's because the record length is 45 years and these return periods exceed that record length. So it's just sort of highlighting that there may be some uncertainty attached to those growth factors. So we can have a closer look at this growth curve here. So this is generalized logistic distribution fitted through the AMAX series for this site. And we can select other distributions as well. So let's have a look at the generalized extreme. We'll use the Al-median technique again. And then we can have a look at this flood frequency curve with both lines fitted through it. So you'll see that the generalized extreme is a slightly flatter growth curve. It estimates less steep growth factors for those higher order events, as we can now see when we select station fittings you can see, rather than a 4.774 growth factor, you've got 4.168 growth factor for that 500-year event. So that's the single-site analysis. This station has 45 years of data, which is quite a lot, but it's probably not enough if we're assessing sort of higher order events. So we probably would look to apply a pooled analysis. And it's brought up this dashboard here. Here you can set the urban threshold, which by default is set to that rural value of 0.03. If we're in Wales, we would increase that to 0.3. So we're creating the pooling group now. It's applied that hydrological similarity equation to find pooling group members that are similar to our target site. So we've got the Itchen at Highbridge, and that had the lowest distance measure. So it's a catchment probably with similar area, similar SAR, and possibly similar FAR and FP extent to our target site. So looking at this pooling group, are there any stations we are going to look to reject? The Tyne at East Linton is the obvious one, and that's because it has an altitude value of minus 0.08, which is fractionally negative, but we would just remove that as a precautionary measure. So we remove that. Now we have got the S at Bridgeway, which is now flagging as discordant. We'll have a closer look at that now. So the way we do that is looking at the pooling group that's been derived, double-clicking on the station, and having a look at the summary statistics for this. So we can have a look at the visual tools, so the flood frequency curve. You can see that it's quite close to a negative altitude based on the generalized logistic, and it is a negative altitude based on the generalized extreme distribution. We can also get a bit of detail on the QMed suitability and the pooling suitability. So there's no gaugings beyond QMed, but all flows contained and rating extrapolation informed by full range of ultrasonic flow meter, and that is thought to be reliable. So it may be appropriate. There is kind of a degree of subjectivity here, whereby you really need to make a decision, but there's not necessarily a right or wrong answer. In this case, we're just going to accept it, just to keep the demonstration length reasonably short. So let's say we accept this pooling group. We can now look at the aggregated growth curve it has derived. So that can be viewed here. So if we look at the fittings, again, this is the same as what we saw for the single site analysis. So just the growth factors there, scaling to those higher return period events. Potentially in this situation, we have more confidence in these because we are using 500 years of station data rather than the 45 years of data being used in the single site analysis. We can also have a look at the graph, which just shows the growth curve as derived using the generalized logistic distribution. And we can also have a look at the flood frequency curve, which is those growth curve factors multiplied by the QMed there. And that just gives you an idea of that. So you can see that that's in QMEX, giving us an idea of the flows. Now, this station, it does have 45 years of data, so it would not make sense really to ignore it completely, especially if it is suitable for pooling, which it has been classed as suitable for pooling in the NRFA. So currently we're just using it for QMed, so we're using the record to derive QMed using the AMAC series, but what we really would probably opt to do is use for QMed and an enhanced single site analysis. So when I click this option here, you can see that the station has been added to the pooling group. It's at the top because it's the most similar to itself. So you can see the distance measure is 0. It has got the highest weighting in the pooling group, and therefore that has an impact on the growth curve. So if you have a look at the growth curve fittings again, that 500-year event went slightly up, I believe, to what it was just based on the pooled analysis. And this is kind of the best of both worlds. So we're incorporating the pooling station, the gauging station data we've got, but we're also supplementing that with the pooled analysis. So we've got a lot of station years in our record. So just a look at a couple of the tools we can use to assess how good this pooling group is. So we can look at goodness of fit, and we can see that it is showing an acceptable fit to the generalized logistic and the generalized extreme distributions. We'll probably opt to use the generalized logistic for the reasons already mentioned. We can also have a look at the heterogeneity. So we can see based on that H2 measure, it's quite a homogeneous pooling group. So it is possible there's a bit of heterogeneity, but really a review of the pooling group is optional. So the final step is to apply urbanization. So we'll apply the urban adjustment factor as we do for Q-med estimation. So you see that Q-med value go up. It's also applied that to the growth curve, reducing the LCV, tending to, and also increasing the L skew. And that will be our final growth curve. And this will be what we are really looking for. This will be our peak flow estimates. Now, when we apply the FEH methods, we typically would compare these against RefH and go forward with one or the other. So that's the end of this training video. I hope you found it useful. More detail on the statistical method and the FEH methods as a whole can be found on our website. Thank you for listening.